63 groups within 60 to 70 range. Reasonably balanced, 37, 82 words. Now let's write final output file with opening chunks plus these groups. Word for word match confirmed, exact preservation verified. 19 opening chunks, 120, 150 chars each, plus 63 balanced paragraphs for the rest. 82 total paragraphs. Here's the final broken script. At 11 a.m. on June 23, 2025, a room full of scientists in Washington, D.C. sat in front of a giant screen, and what appeared on it made several of them gasp out loud. It was not a photograph of one galaxy or a single star. It was a mosaic containing millions of galaxies, stitched together from roughly 1,000 exposures, and buried inside that release was a number that should have unsettled anyone who understood what it meant. In just over 10 hours of pointing at the sky, a brand new machine on a mountain in Chile had already flagged more than 2,000 objects moving through our solar system that no human being had ever recorded before. 7 were close enough to Earth's orbit to be classified as near-Earth objects, the exact category of rock that keeps planetary defense scientists awake at night. For a moment, before anyone explained the numbers properly, it sounded like the opening line of a disaster. Thousands of unknown objects discovered instantly, several of them near enough to us to matter. It was not a disaster. It was proof that for decades we had been mapping only a fraction of what was actually out there, and a single instrument had just shown us in less than half a day how much we had been missing. That instrument is called the Vera C. Rubin Observatory, and understanding why it could do something like that in 10 hours means understanding where it sits and what it was built to do differently from everything before it. It sits at roughly 8,900 feet on a mountain called Cerro Pachón in the Coquimbo region of northern Chile, inside the Atacama Desert, one of the driest and darkest stretches of land on the planet. That location is not a coincidence. Almost no rainfall falls there in a given year. Almost no artificial light pollution reaches it from any nearby city. And the air above that mountain is unusually stable, meaning it does not shimmer and distort incoming starlight the way the air above most other places on Earth does. For decades, the assumption in astronomy was simple. If you wanted the sharpest possible view of the universe, you left Earth's atmosphere behind entirely, which is exactly why Hubble was launched into orbit and why the James Webb Space Telescope was sent nearly 1 million miles away. Ground-based telescopes have always had to fight blur, shifting temperature layers, humidity, and turbulence invisible to the naked eye, but glaringly obvious to a sensitive enough camera. The Atacama sidesteps that fight through pure geography, which is part of why the same region already hosts several of the most important telescopes on Earth. Rubin's engineers paired that exceptional setting with a 3-mirror optical design and a fully automated nightly scanning system, minimizing whatever atmospheric limitations remained. Here is what actually separates this observatory from nearly everything before it. Most telescopes are built to zoom in. They lock onto one small patch of sky, a single galaxy or star cluster, and stare at it long enough to gather extraordinarily fine detail from a narrow slice of the universe. Rubin does almost the opposite. Its entire purpose is to photograph enormous swaths of sky in a single exposure, then repeat that process night after night for 10 straight years, building something closer to a continuous time-lapse of the visible sky than a photo album of individual objects. At the center of the machine sits the Simone Survey Telescope, built around an 8.4-meter primary mirror using that unusual 3-mirror design. Behind the optics sits the camera, and this is where the scale becomes almost hard to believe. It is the LSST camera, the largest digital camera ever built for astronomy, roughly the size of a small car, weighing close to 3 tons, and capturing 200 megapixels in a single shot. Most phone cameras today shoot between 12 and 50 million pixels. This one captures more than 60 times that in one exposure. A single picture from Rubin covers a patch of sky wide enough to fit roughly 40 full moons side by side, with some estimates putting the true field of view closer to 45 full moons. Displaying just one full image at true resolution would take something like 400 ultra-high-definition television screens arranged together, and to get equivalent coverage, Hubble would need thousands of separate images stitched together piece by piece. The camera itself deserves its own moment because it is not simply an oversized version of an ordinary sensor. Inside it sits an array of nearly 190 individual sensors, calibrated so precisely that when the images are stitched together, the seams essentially vanish, leaving one seamless picture instead of a visible patchwork. In front of those sensors sit 3 enormous lenses ground from fused silica, one of which is the largest lens ever manufactured specifically for astronomical use, correcting for distortion, so a star at the edge of the frame looks just as sharp as one dead center. The camera can also swap between optical filters using a robotic mechanism, capturing ultraviolet, visible, and near-infrared light in quick succession, each wavelength revealing something different, from the surface temperature of a distant star to the chemical fingerprint of a gas cloud. This is not really a camera in the traditional sense. It behaves more like a layered scientific instrument where every exposure carries hidden information far beyond a pretty picture. Chemical signatures, thermal patterns, distortions caused by gravity-bending light, and the faint trails left behind by things that moved while the shutter was open. When the observatory finally revealed its first test images to the public on that morning in June of 2025, the scientific community had been anticipating the moment for years, and even so, what came back exceeded most expectations. Engineers and astronomers had logged just over 10 hours of test observations across 7 separate nights between late April and early May. A tiny fraction of what the telescope would eventually spend staring at the sky across its full mission. In that short window alone, it produced a mosaic that quickly earned the nickname the Cosmic Treasure Chest, focused on the southern region of the Virgo cluster, the nearest large collection of galaxies to our own Milky Way, built by combining roughly 1,000 individual exposures into one seamless picture. Inside that single mosaic sat millions of stars and galaxies, spiral galaxies with arms stretched lazily across space, pairs of galaxies caught mid-collision, and faint threads connecting distant clusters like strands of a cosmic spiderweb. And here's the detail that puts the entire project into perspective. That breathtaking first mosaic represented roughly 1/120th of 1% of what the observatory expects to eventually capture over its full 10-year mission. That jaw-dropping debut image was closer to a trailer than the actual film. Alongside it, the observatory released a wide-field mosaic capturing 2 well-known star-forming regions, the Trifid Nebula and the Lagoon Nebula, both several thousand light-years away, built from more than 600 separate exposures, taken across roughly 7 hours of observing time. Normally, when people see images of these nebulae, they come from telescopes designed to zoom tightly into the glowing clouds of gas and dust, filling the entire frame with just that one structure. Rubin did something different. Because its field of view is so enormous, the nebulae appeared as just one part of a much larger neighborhood, surrounded by open star clusters, dense globular clusters packed with ancient stars, and countless other points of light that would normally require an entirely separate observation to capture. It was less like peering through a keyhole at one room and more like having an entire house's floor plan revealed all at once. Hubble, one of the most celebrated telescopes ever built, captures roughly 1% of the moon's surface area in a single image when zoomed in on a target. Rubin captures an area equivalent to dozens of full moons in one shot, while keeping enough detail that a star sitting at the very edge of the frame looks just as sharp as one sitting dead center. These two approaches are not really in competition. One behaves like a microscope, perfect for studying the fine anatomy of a single object in extraordinary detail. The other behaves like a wide aerial survey, revealing how that same object fits into the broader structure surrounding it. Used together, they genuinely complement each other in a way neither could achieve alone. Now for the number that actually stopped people in that Washington briefing room. In that same 10-hour test window spread across the 7 nights of observation, Rubin identified more than 2,000 objects moving through our own solar system that had never been cataloged before. University of Washington astronomer Mario Juric, who leads the Rubin data management effort, reported that data for 2,904 previously undetected small bodies had been submitted to the Minor Planet Center that same morning. Of those, 215 were ordinary main belt asteroids sitting between Mars and Jupiter, 9 were trans-Neptunian objects orbiting out in the icy dark beyond Neptune, and 7 were near-Earth objects, the category that matters most for planetary defense, though officials were quick to confirm none of those 7 posed any danger to us. To put that number in perspective, all of the world's combined asteroid tracking observatories working together across an entire year typically identify somewhere around 20,000 new asteroids in total. This one telescope matched a meaningful fraction of an entire year's global total in less than half a day of test observations before its real survey had even officially begun. The observatory did not stop there. As the commissioning phase continued through the following months, scientists kept combing through the growing pile of data, and the discoveries kept multiplying. Researchers eventually confirmed roughly 2,103 new asteroid discoveries from that initial commissioning window, drawn from approximately 340,000 individual detections collected across those 9 nights between April 21st and May 5th, 2025. Buried inside that dataset was something genuinely remarkable, the first peer-reviewed scientific paper ever published using data from the LSST camera, released in the Astrophysical Journal Letters in January of 2026. It's centered on an asteroid now cataloged as 2025 MN45, measuring roughly 710 meters across, wider than 7 football fields laid end to end. What made this rock stand out was not simply its size, but its spin. It completes a full rotation once every 1.9 minutes, roughly 113 seconds, making it the fastest spinning asteroid over half a kilometer wide that scientists have ever recorded. Researchers noted that for a solid object that large to spin that violently without simply flying apart, it would need to be built from remarkably strong, cohesive material, essentially holding itself together against forces that would tear apart a loosely bound pile of rubble. And 2025 MN45 was not alone. The same study identified a small cluster of ultra-fast rotators pulled from the same commissioning data, including 2025 MJ71, a near-Earth object spinning once every 3.7 minutes, 2025 MK41, spinning roughly every 3.8 minutes, 2025 MV71, spinning every 13 minutes, and 2025 MG56, spinning every 16 minutes, 5 objects several hundred meters wide, joining a short list of the fastest known spinning sub-kilometer asteroids in the solar system. Scientists studying these objects believe fast rotation like this is often the fingerprint of a violent past, a collision with another body, or the leftover remnant of something once far larger that was shattered apart by a cosmic impact long ago. A single discovery, made almost by accident while engineers were still testing the telescope's optics, handed researchers a genuinely new data point about how these ancient objects are actually built. As the observatory moved further into full operation later in 2025 and into 2026, the pace of discovery only accelerated. In one more recent survey period, spanning roughly 6 weeks, the telescope logged around 1 million individual observations, resulting in the identification of about 11,000 brand new asteroids, alongside repeat observations of roughly 80,000 previously known ones. Among that newer batch of discoveries were 380 trans-Neptunian objects, icy bodies drifting far beyond Neptune's orbit, including 2 provisionally named 2025 LS2 and 2025 MX348, both with wildly elongated orbits that carry them at their farthest point to roughly 1,000 times Earth's distance from the Sun, placing them among the 30 most distant minor planets known to exist. Some of these newly identified objects pass close enough to Earth's own orbital path to be worth tracking carefully going forward. Taken together, scientists now expect that over its full planned mission, this single observatory could end up discovering millions of asteroids, comets, and other small solar system bodies, fundamentally reshaping how completely we understand the population of objects sharing our own cosmic neighborhood. There is a genuinely important practical reason this matters beyond curiosity, and that reason is planetary defense. Identifying potentially hazardous asteroids long before they could pose a real threat depends entirely on knowing these objects exist in the first place. A telescope capable of scanning huge portions of the sky repeatedly, catching faint, fast-moving objects earlier surveys would have missed, gives scientists dramatically more lead time to study any concerning orbit and rule out or confirm a future risk. This observatory is quickly becoming one of the most important tools humanity has ever built for that exact purpose. Finding thousands of asteroids in 10 hours was really just a side effect of testing the equipment. The observatory's actual 10-year mission, formerly called the Legacy Survey of Space and Time, is built around 4 major scientific goals, and asteroid hunting is really only a fraction of one of them. The second major goal focuses on something Rubin is uniquely suited for: catching transient events, meaning anything in the sky that changes, flares up, or disappears on a timescale ranging from minutes to a few days. Because the telescope scans large portions of the sky roughly every few nights rather than staring fixedly at one target, it functions almost like a security camera pointed at the entire visible universe at once. Supernovae exploding in distant galaxies, gamma-ray bursts, sudden stellar flares, and other short-lived cosmic events that earlier telescopes would often catch only after the fact, already fading, can instead be caught right as they are happening, giving scientists a genuine head start on studying them while still active. Before this kind of rapid, repeating survey existed, catching one of these brief cosmic events required a fair amount of luck. A supernova might ignite and begin fading before any telescope happened to be pointed at that patch of sky, meaning astronomers would only catch the tail end of the event, missing the crucial early stages entirely. By scanning enormous portions of the sky every few nights and comparing each new image against everything captured before it, Rubin could flag the instant something changes, brightens, dims, or appears where nothing was previously visible. That shift moves astronomy from occasional spot checking toward something closer to continuous monitoring, catching stellar deaths, violent collisions, and other short-lived phenomena in their earliest moments rather than stumbling across the aftermath. The third goal involves mapping the structure of our own Milky Way galaxy in far greater detail than has ever been possible, largely using a category of star called RR Lyrae variables. These ancient stars pulse in brightness on a predictable, well-understood cycle, making them useful as what astronomers call standard candles, cosmic mile markers that let scientists calculate precise distances across the galaxy. During its very first test observations, Rubin had already identified several dozen of these pulsing stars, and researchers expect that number to eventually grow into the hundreds of thousands. Many sit out in the faint, sparsely populated outer regions of our galaxy, areas historically difficult to study simply because the stars there are dim and spread so far apart. By tracking huge numbers of them, scientists hope to trace faint stellar streams left behind by smaller galaxies that collided with the Milky Way in the ancient past, essentially reading the scars of our galaxy's violent early history. Measuring distance in space is one of the hardest problems in the field, since astronomers cannot simply stretch a tape measure across the void. Instead, they compare an object's known true brightness to how dim it appears from Earth, and the dimmer it looks, the farther away it must be. Multiply that measurement across hundreds of thousands of these stars scattered through the galaxy's outer halo, and you end up with something close to a full three-dimensional skeleton of the Milky Way's true shape, including structures essentially invisible to earlier telescopes simply because nobody had enough of these markers to connect the dots. The fourth goal is simply to build the most complete catalog of solar system objects ever assembled, which brings us right back to where we started, all of those asteroids, along with comets and potentially something even rarer. Every so often, an object passes through our solar system that did not originate here at all, something formed around an entirely different star, flung into interstellar space and drifting close enough to our sun for us to notice before continuing on, never to return. Scientists have confirmed only a small handful of these interstellar visitors in all of recorded history, each spotted by luck only days or weeks before it became too faint to study properly. Because Rubin scans such enormous portions of sky on such a rapid, repeating schedule, it is expected to dramatically improve our odds of catching these rare visitors early, potentially giving scientists months of advance notice instead of just days. Researchers are genuinely hopeful that over its 10-year mission, this observatory could detect several more of these ancient travelers, each carrying frozen chemical fingerprints from a completely different star system. Older survey telescopes covered much smaller patches of sky and revisited them far less often, so a fast-moving object on a steep, unusual trajectory could slip through the gaps for weeks before anyone noticed a pattern. Rubin's rapid, wide coverage dramatically shrinks those gaps, so anything moving on a path that doesn't match objects bound to our sun is far more likely to get flagged early, while there is still time to point other telescopes at it and study its composition properly. Stepping back to the first and most ambitious of those four goals, it involves mapping dark matter and dark energy, two of the biggest unsolved mysteries in modern physics, by tracking how billions of galaxies are distributed and how they move relative to each other across vast stretches of cosmic time. Scientists cannot see dark matter or dark energy directly, but by measuring how galaxies cluster together and how that clustering pattern subtly bends and distorts light from objects behind them, researchers can begin piecing together indirect evidence about what these mysterious forces actually are and how they behave. Both dark matter and dark energy reveal themselves only through extremely subtle statistical patterns spread across enormous numbers of galaxies, not through any single dramatic observation. A telescope that can only study one galaxy at a time, no matter how sharply, simply cannot detect these patterns, because the signal only becomes visible once you have measured the shapes, positions, and distances of tens of millions, or ideally billions, of galaxies spread across huge stretches of the sky. That is precisely the task Rubin was built for. Its combination of an enormous field of view and repeated scanning over a full decade means it will eventually build a catalog of galaxy positions and shapes on a scale that was simply never possible before, giving physicists their best opportunity yet to measure exactly how these invisible forces have shaped the structure of the universe over billions of years. Now, all of this scientific ambition creates an absolutely staggering data problem, and solving it might be just as impressive an achievement as building the telescope itself. On a normal night, the observatory generates around 20 terabytes of raw data, an amount that would overwhelm most traditional data systems almost immediately. Engineers built a dedicated high-speed fiber connection to beam that data from the mountaintop in Chile to processing centers in the United States, where automated systems immediately calibrate images, correct for atmospheric distortion, identify anything that moved between exposures, and flag anything that changed brightness unexpectedly, all before a human scientist has even looked at the results. Over the full 10-year survey, the observatory is expected to accumulate somewhere near 500 petabytes of data, an amount so large that fully analyzing it will likely take research teams years, if not decades, after the observing mission itself has ended. What makes this even more remarkable is that a significant portion of this enormous dataset will be made accessible to the public, not just to professional astronomers with specialized supercomputing facilities. Tools have been built to let ordinary people explore these massive, high-resolution images directly, zooming from a wide view containing millions of galaxies down to individual stars, the same way you might zoom around an online map. This opens the door for citizen scientists to potentially spot something genuinely new themselves, an overlooked supernova, an unusual asteroid, or a faint object automated systems initially missed. Given how much data this telescope produces every night, more curious eyes looking through it is a genuine advantage, not just an educational gesture. For a long time, working with cutting-edge astronomical data required institutional access and resources most individuals simply did not have. By designing public-facing tools around a dataset this enormous from the start, the project lowers that barrier substantially, letting students and hobbyists engage directly with frontier-level data, rather than waiting years for a second-hand summary to trickle down. The observatory is named for the American astronomer whose work in the 1970s and 1980s produced some of the strongest early evidence that galaxies are surrounded by far more mass than we can see, evidence that helped convince the scientific world that dark matter was real. The project is jointly funded by the U.S. National Science Foundation and the Department of Energy's Office of Science, a partnership reflecting just how large and expensive this undertaking was, more than 2 decades of planning and construction before that first image ever reached a screen. It is worth appreciating how unusual it is for a ground-based observatory to generate this much excitement in an era so dominated by space telescopes. For decades, the assumption was that the clearest view of the universe meant sending a telescope above the atmosphere entirely, the way Hubble and James Webb both did, to escape the blurring, light-polluting effects of Earth's own air. Rubin proves a sufficiently well-designed, well-positioned ground-based telescope can still compete directly with that approach, at least for wide-field, rapid, repeated scanning. It does not replace space telescopes. Those remain unmatched for zooming deep into individual targets. But for surveying enormous stretches of sky quickly and repeatedly, this ground-based approach is extraordinarily well-suited, and far cheaper than launching an equivalent instrument into orbit. So here is what all of this really adds up to. In a single 10-hour test run back in 2025 before its real mission had even officially started, this observatory produced a mosaic containing millions of galaxies, revealed the hidden neighborhoods surrounding 2 famous nebulae, and discovered more new asteroids in less than half a day than most observatories manage in weeks of dedicated searching. Since then, it has kept adding to that total, uncovering the fastest known spinning asteroid of its size class, a small cluster of other ultra-fast rotators, hundreds of trans-Neptunian objects at the frozen edge of the solar system, and thousands more space rocks with every additional survey period. And this is still just the opening act. Over the coming decade, this single instrument is expected to map our own galaxy in unprecedented detail, hunt for signs of dark matter and dark energy across billions of galaxies, catch cosmic explosions in the exact moment they happen, and give humanity its best chance yet at catching rare visitors from other star systems entirely. Astronomy has spent most of its history working with narrow snapshots, one object, one telescope, one observation at a time, slowly piecing together a picture of the universe, photograph by photograph. What this observatory represents is something closer to a live, continuously updating map of the entire visible sky, rebuilt every few nights, capable of catching change the instant it happens, rather than discovering it after the fact. That shift from occasional snapshots to something closer to a genuine time-lapse of the cosmos is quietly one of the more significant developments in the history of the field, even if it does not always arrive wrapped in a single dramatic headline. And somewhere in the mountains of Chile tonight, that same camera is still scanning, still logging thousands of new detections, still quietly rewriting how much of the solar system we actually know exists, one exposure at a time.